As we've begun our new unit on solutions and IMAs, intermolecular attractions, one of the labs that you performed was the paper chromatography lab involving food colorings. And in this lab, um, we used three different solvents and you were examining the impact of those solvents on the ability to separate out the mixtures of dyes that were potentially in each of the food colorings. The first the first solvent that you used was really an aqueous solution where we put a little bit of sodium chloride into the solution to accentuate the polarity of that solution. Obviously, you can see here the sodium chloride lattice structure, and of course when you dissolve it in water, those ions will dissociate and they contribute to the polarity of the solvent, and as it is absorbed by the paper and moves up the paper, it will tend to interact with molecules that were also polar. Your second solvent was propanol. Okay, and you can see from its structure that it is a covalent compound, and on the central carbon you can see a hydroxyl group, which gives it a little bit of polarity, but not nearly as much as you had in the water and the salt solution. The third solvent was a solution of acetic acid. You can see on the right hand side, you can see the carboxyl group. You can see that those bonds between the carbon and oxygen and the oxygen hydrogen, those are polar covalent bonds, and they contribute to the polarity of this molecule. So not quite as polar as water, but still a high degree of polarity nonetheless. So you put your dyes, your food colorings, onto the chromatography paper, the filter paper that we're using, and you set them down into these three solvents, and you watch the progression of the solvent up the paper, and you saw how it started to interact with the dots that you had made. And now if we look at the structures of the four dyes that are actually in most food colorings, you can kind of get an idea of what their polarity is. Here's blue number one, and you can see that it's a fairly large molecule, that large portions of it are nonpolar. But you see those sulfate groups. There's very clearly three sulfate groups. You've got a couple of amino groups towards the center, and that lends a larger degree of polarity to this molecule. Red number 40, on the other hand, still a degree of polarity, maybe not quite as much as in the blue. Again, you can see on the far left and the far right you have sulfate groups. You can see sodium ions associating with that. In the center you've got that those amino groups connected to each other, the two nitrogens double bonded, and right below that you can see the hydroxyl group. So not quite as large of a molecule, a degree of polarity, but again mostly nonpolar. The third dye, yellow 5, again a smaller molecule compared to the blue dye, but again you can see sulfate groups at the far ends and a hydroxyl group in the middle. Again, you've got those rings in there, those rings of carbons connected to each other, lending a large degree of non-polarity to those sections. And then finally red 3, again a lot less polarity. There are those oxygens that are in the rings and coming off the edges of the rings that lend some polarity. You can see how sodium ions have associated with it. So you can see in all four of these that they're kind of mixed molecules, mostly non-polar, but they do have functional groups, hydroxyl groups, amino groups, sulfate groups that lend some degree of polarity and will affect how they interact with the solvents. And finally, when you look at the strips, you can see that, in fact, uh, many of these dyes, many of the food colorings, I should say, uh, are actually mixtures. Okay, whether it's intentional or not. The green, obviously, there's in this situation at least there is no green dye. There's actually a yellow and blue dye. You can see that very clearly in both of the strips here. The blue has some red in it as well as the blue dye. Even the red itself is actually a mixture of red 3 and red 40. Um, Yellow generally pretty much is pure, uh, though in the bottom strip you can see a little bit of probably some contamination of red from the manufacturing process. And then my last two strips here, this is a situation where I ran it with acetone also, and again you get slightly different profile in all of these, um, but it does. And finally, this one I think is really nice because you can see the acetone on the bottom. You can see mostly the red 3 migrating, that light pink color migrating, which kind of makes sense if you think back to the structures that we looked at early on in the slideshow.